So Megan McArthur was born in Hawaii, and then she came over to California, grew up in Northern California, came down to UCLA, where she got her BS in Aerospace Engineering. Even as a teenager, she dreamed of being an astronaut, and so it made a lot of sense that as soon as she graduated with her degree in Aerospace Engineering, she went into oceanography. And while she was at the Scripps Institute of Oceanography, she conducted graduate research in nearshore underwater acoustic propagation and digital signal processing, and eventually served as chief scientist during at-sea data collection operations. She planned and led diving operations to the seafloor and participated in a range of in-water instrument testing and development. She also volunteered at the Birch Aquarium at Scripps, conducting educational demonstrations for the public from inside a 70,000-gallon exhibit tank of the California kelp forest. In 2000, though, she returned to that teenage dream of being an astronaut and was selected as a mission specialist by NASA in July of 2000, and she reported for training in August of 2000, doing all those things that you do to get ready and prove yourself ready to be an astronaut. And she was a member of the STS-125 mission to service the Hubble Space Telescope. So, I mean, basically, a couple of years ago, I saw Megan speak at our engineering awards dinner, and I realized that she had to come and speak at a freshman orientation. And I'm so happy that we have her here today. And then in between that time and this wonderful moment where she's about to speak to us, I had the opportunity to take my kids to an IMAX film on the Hubble Space Telescope mission. And maybe some of you have seen it and got to see Megan in the movies working on the Hubble Space Telescope. And I'm just so excited today to be able to bring you Megan McArthur.
Thank you very much, Prospective Bruins. I'm really glad to be here with you today. I actually used to work in Royce Hall. I worked for the Central Ticket Office when I was a student at UCLA, so I spent a lot of time in the box office there out front, and I used to come in here to see some of the performing arts events that they would hold here and still do. It never occurred to me that I might be on stage attempting to provide entertainment for an audience of this size, so I hope you'll bear with me. I also hope you will come back to see some performing arts events while you're here. I know you're engineers, but trust me, it's good for you. And I promise you, though, that this will probably be the only time that you'll ever watch a rocket launch from in here, and I hope you enjoy that. The other thing I was thinking about when they invited me to speak is that I graduated from UCLA in 1993, which I did a little bit of math and figured that's probably right around the time most of you prospective students were being born. So I wondered, what could I tell this group of students that's relevant to your education today? You've already made the decision that you want to be an engineer, so you know about the many benefits of being an engineer or studying to be an engineer. You're going to be training your brain to think logically, to analyze complex systems, and to solve technical problems. Now, you've heard today about the laundry list of problems that the world will expect you to be able to solve as engineers of the future. We're talking about providing clean water to people who don't have access to it, finding practical sources of alternative energy, and my personal favorite, enabling human presence beyond low Earth orbit. So if you could get to work on that, I'd appreciate it. Of course, these are all skills that are going to benefit you no matter what your future career will be. I know doctors, scientists of all types, lawyers, businesswomen who started their first initial education was in engineering. So you've made a good choice right off the bat. The fact that you're here at UCLA today means that you're exceptionally smart and you're thinking in the right direction about where to go in the future. You've heard also about the fact that you're going to receive an education here that will give you a solid foundation in the fundamentals of science and engineering in courses with world-class faculty such as you see up here today. But one of the most important things that I learned here first, which is so crucial in my current profession, is the ability to work as a team, as part of a team to solve technical problems. In 1993, I participated in an independent study project with about half a dozen other engineers to build a human-powered submarine and race it off the coast of Florida. Now, you might be wondering why a group of aero engineers decided to build a submarine, but that's a story for another day. If you catch me afterwards, I can tell you all about it. But the experience that we had of designing, building, testing, and racing that submarine is one that I always come back to when people ask me, well, what was your path to becoming an astronaut? What were the pivotal moments in your education? That was a hands-on, practical experience involving a budget and a schedule, a lot of fun, and not a lot of sleep. In fact, as we were nearing the race date and working around the clock in our lab in Engineering 1, I made the mistake of collapsing in a chair outside the lab and trying to get a quick nap. I woke up just a few minutes later and found out that my teammates had written all over my face with black magic marker. So the lesson I learned there was that no one on the team sleeps until all the work is done. The support we received during that time from the engineering school and the contacts they helped us make with industry were absolutely invaluable to our project and to our education as a whole. We would not have succeeded at all without the many technicians and machinists from the university labs that also loaned us their expertise. It is crucial that you learn this team approach to technical problem solving, how to be an effective team member at the start of your engineering career. It is, of course, how engineers all over the world solve the problems that are requiring solving right now, on and off the world, actually. In 2009, as you heard, I worked in low Earth orbit aboard the Space Shuttle Atlantis as the flight deck engineer and the robotic arm operator to the final servicing mission for the Hubble Space Telescope. Our tasks included replacing hardware to extend the life of the telescope, upgrading some scientific instruments, and performing the first ever card-level repair of scientific instruments in space. Accomplishing this took a lot more than the 7 of us on the crew, of course. The preparation for these intricate, never-before-attempted repairs required a huge team of scientists, engineers, technicians, and operators working together to develop equipment and procedures. We had over 100 special-built tools just for this mission for our unique tasks that were designed by a collaboration between engineers, technicians, and the spacewalkers themselves. Not to mention the hundreds of engineers and technicians that get the orbiter ready to fly and monitor the systems while we're in space. Once on orbit, we had all kinds of unexpected problems with the vehicle and with the telescope. Stuck bolts were really our nemesis, and we had a few master alarms go off during the launch itself, which you'll see during the movie. Our spacewalks, actually, several of them went very long, record-setting, over 8 hours. They're usually around 6 hours. And when our spacewalkers came in every day, we did 5 of these in a row, we would have this huge explosion of gear. And you don't go to bed until all this stuff is put away. That's a lesson I learned early on here at UCLA. I can't imagine what these guys would have done to me if I tried to fall asleep before all the work was done. But working together, we were able to get through all of these problems, and we'll show you some of that here in just a minute. I'd like to show you some home movies of our spaceflight, basically. And Erky, if you could get that video up for me, I'd appreciate it. But what I'd like you to look for in this video are some examples of how all the different kinds of technical problems that we faced and the teamwork involved in solving those problems real time. So I think probably everybody here has heard of the Hubble Space Telescope. It's been in space for over 20 years now, and that's an image of it there going around the Earth. It goes around the Earth every 90 minutes. It's about 300 miles up, and it's, of course, responsible for some of the remarkable images that you have seen of our own solar system, planets in our own solar system, of galaxies far, far away, so far away sometimes that it's hard to even imagine how far away they really are. Taught us many things about the universe, the expansion rate of the universe, the existence of black holes. There's good evidence for that from images from the telescope. Unfortunately, due to the fact that it's over 20 years old, it had a lot of problems. Basically, only one remaining scientific instrument was working at the time of our launch. So it needed a huge overhaul. We were going up there to replace batteries, to replace guidance sensors, navigation sensors, take out old scientific instruments that weren't needed anymore, put in new state-of-the-art instruments, as well as repair instruments in space that were never designed to be repaired in space. So we had a huge workload, and really years were spent, hundreds of engineers designing the tools and methodology that we would use to do these repairs. Since we can't take the telescope into a repair shop on Earth, our repair shop is basically the Atlantis Space Shuttle. 7 of us went up there. We spent about 2 weeks up there. We have everything from pilots to geophysicists and astrophysicists and oceanographer on the crew. There's me. I'm the robotic arm operator. Yeah, go Bruins. Thank you. So it was my job during the spacewalks to fly the spacewalkers around on the end of the arm so they could reach their position that they needed to work in. So that's kind of the overview. We had 2 shuttles on the launch pad, never seen before, one ready to come and rescue us if we had any problems with ours that we couldn't solve. Important to get in the right shuttle. This one is Atlantis. And we were very excited that morning. You can see us, we're walking out. You may not be able to hear me talking once the space shuttle gets going, but this is mission control. They're all monitoring the systems there, making sure we're ready to go. Right at liftoff, however, we had a master alarm, which is, as the word would imply, very alarming, and you'll hear us talking about that in the early phases.
2, 1, and liftoff of Space Shuttle Atlantis. Final visit against the vision of Hubble into the deepest grandeur of our universe.
Houston Atlantis, small program with the FCS channel.
So we had something called an FCS channel that failed. Fortunately, we have 4 of them, redundant channels that operate the flight control systems, and we were good to go to continue, but you're not expecting to hear a master alarm right at liftoff. We're rocking and rolling at this point, shaking pretty hard in our seats as the solid rocket boosters are doing their job getting us off the surface of the Earth. We're getting faster and faster. We go from 0 to 26 times the speed of sound in 8.5 minutes. So you can imagine what that acceleration feels like. We spend hundreds of hours in simulators prior to the mission. It really doesn't prepare you at all for what this actually feels like. The solid rocket boosters burn for about 2.5 minutes, then they are spent. They fall back to the Earth. That's what's happening right there. That's a camera on the booster looking back at the orbiter continuing into space. The boosters fall into the water. They're collected, cleaned up, and used again. We do recycle at NASA. That's the main engine tank. That's the gas to fire the main engines. It is spent after 8.5 minutes. That does burn up in the atmosphere and fall back into the ocean. Once we're in orbit, we open up the payload bay doors. All the orange-covered equipment in there is the new equipment that we're going to put into the telescope. The first job we have to do is go and find that telescope in orbit. We have to match rates with it, basically do a series of rendezvous burns and catch up to it so that it looks like we have no relative motion between the space shuttle and the space telescope. Again, both objects, both spacecraft going around the Earth at 17,500 miles per hour. We fly up underneath the telescope, and then I reach out with the robotic arm and grab a hold of it. This is a cartoon kind of showing you what that looks like. Once I have a hold of it, I put it on basically a lazy Susan at the back end of the payload bay, and it gets locked into place so we can go to work on it the next day. So here you'll see that operation taking place real time. That's our commander. He's called Scooter on the left in the green of Top Gun fame. And he is basically driving the orbiter up next to the telescope. I'm giving him information on the range and the range rate. As we close with the telescope, that's the bottom of the telescope there. We're flying up underneath it. And once I have my target in sights on the robotic arm, I tell him that I like the position, and I go ahead and reach over and grab hold of the telescope. So this is a camera on the end of the robotic arm looking at the bottom of the telescope as we fly up underneath it. So there's the target there. There's a pin sticking off the side of the telescope, and I line up my sights on that target and drive in. It's a little bit like a video game, but very, very, very slow motion. Obviously, I don't want to tip the telescope at all or bump it in any way to generate a relative motion between us and the telescope. It's huge. It's about the size of a bus, and it's only a few feet away from us at this time. So this was kind of my first big moment. I was pretty excited about it and pretty happy to have completed it successfully, as you'll see here in just a second. That's the target, and I'm about to pull the trigger. You'll see a little bit of motion as the snares close over that pin, and we have a good solid grip on the telescope.
Houston Atlantis. Hubble has arrived on board Atlantis with the arm.
So there's me getting a handshake from the commander. Glad I didn't screw that up, and we can all go to work the next day and do our spacewalks.
Well, it's great to be back with the telescope.
So I've got a hold of it there. We park it in the aft end of the shuttle's payload bay. You can think of it kind of like the pickup truck, a bed of your pickup truck. We're in the cab of the pickup truck looking out the rear windows into the bed of the truck. I talked about an explosion of gear. You can see that here. This is basically our entire living space other than the flight deck. All of those giant white bags are full of the tools I was telling you about, and of course the spacesuits. That's a space helmet. Our pilot, Ray J, putting that through into the airlock. The airlock, of course, is a tiny little room. We get the guys in their suits, suck all the air out, and then they come out the other side into the payload bay. This is my friend Drew, a geophysicist, doing his first spacewalk. I love this picture because you can see the reflection of the Earth in his helmet there and a big grin on his face. So Mike Massimino, also a spacewalker, but today his job is to choreograph the work going on outside with the other two, and there's me getting ready to drive the robotic arm around. The very first task that we were going to do was to replace the Wide Field Planetary Camera 2. This is a famous image I'm sure you've all seen called the Eagle Nebula or the Pillars of Creation. Star formation is going on in here, and it's an iconic image that I think everyone is familiar with. This was the only scientific instrument still working on the telescope. We figured it'd be a pretty simple replacement with the upgraded technology. This is an image in the training pool. It's a radial instrument. You pull the old one out, a couple of bolts, you slide the new one in. Unfortunately, it didn't go quite as planned. The bolt that drives the instrument in and out got stuck, wouldn't move at all. So if we broke that bolt, the instrument, the only working instrument in there at the time, would be stuck in there forever and not be able to be upgraded. So a lot of tension, a lot of feeling about this going on. And I'll pause so you can hear this.
And wide field stays in.
So he says if we break this bolt,
what John said is correct.
Wide field stays in. So this is a group of engineers on the ground working in the back room at Mission Control. These are the folks that designed, built, tested, and taught us how to install this piece of hardware. You can see how nervous they are about the fact that this may never happen. And so they're all waiting to make sure that Drew doesn't break this bolt and they have a successful removal of this instrument.
Move it out. 4. Great job. Great news.
So that's their reaction. That's Dave Lacrone. He was the senior project scientist for this thing. He told us later that took about 5 years off his life that day. And he retired shortly after we landed, so there you go. But here's the choreography that happens. Basically, you pull that radial instrument out, we temp stow it over the side of the orbiter, we get the new one out of that orange carrier that you can see, and then I fly Drew back into position to reinstall it. So you can see him basically hanging out on the end of the arm while I fly him into position to do all of these different activities. So the arm moves pretty slow, but we had trained a lot to make it as efficient as possible. You see it's nighttime now. We go through a day-night cycle every 90 minutes as we go around the Earth. So they just turn their lights on and they keep going. Getting ready for other activities, you know, he would just work on his tool stanchion as I was flying him around, so we made it efficient that way as well. The next day, we're going to do it all over again. Here we are getting the tools ready for the next day's activity. We trade spacewalking teams. The 2 mics were going to go out the next day, and we did this back and forth for 4 days. You can see them coming out of the airlock there, getting ready. Their task on the 4th day was an instrument called STIS. It's a Space Telescope Imaging Spectrograph, and it is used to detect black holes. It also can detect the composition of extrasolar planets, which is pretty amazing. It was, at the time it failed in 2004, it was the most highly requested instrument on the telescope, so very popular with the scientists that used it, and really a big disappointment when it failed. And so engineers worked overtime to try to develop a fix for how we could get inside this box, because they didn't have the time or the money to develop a whole new box to replace it. This is an image showing basically proof of black hole's existence. You see swirling gas basically being sucked in by this black hole. So really a very valuable instrument, a very highly desired to get it recovered. Unfortunately, this box, which is about the size of a refrigerator, had a panel on it that needed to be removed, kind of like your home computer. This one had 111 tiny torque-set non-captive fasteners. You can imagine if any one of those got loose inside the telescope, it's game over. We're not using it anymore. So they developed this thing called the Fastener capture plate that they would stick on the front of it. But this handrail had to come off first before they could even put that plate on there. Handrails are designed to be taken off EVA. They thought this would be really simple, but again, it didn't quite work out that way. The screw head stripped, and this was the solution that the engineers came up with.
Okay, we're ready.
Real time.
Okay, man, you have a go. Here we go.
So sometimes it really just does take brute strength.
Okay.
You can hear how calm Mike sounds at all this, but you can imagine how frantic he was when he realized that, again, the very first step, the part that we thought was going to be easy, wasn't working out quite right. So once they had that handrail off, they could put that blue fastener capture plate on over this big computer. Then as he backed each individual tiny screw out, it is captive between that blue plate and the plate that's coming off the front of the computer. So very incredibly efficient way to do it, but very intricate, and this was the part we all thought would be very tricky, was removing all of those little screws. But that went really smoothly, and they were able to take that card out and replace it. And you can see how relieved Mike is at the end of the day there. He was pretty thrilled that it had all gone very well. So basically, that was, we did 5 days of spacewalks. We changed out a whole series of instruments. Those were 2 of the trickiest ones that presented problems real time that we weren't expecting, but we had a great team on the ground that was able to help us work through that. That's John Garnsfeld. He's been up to the telescope 3 times, given a little pat goodbye before I pick it up with the robotic arm and toss it out over the side. We don't do it quite that cavalierly, of course, but we have to time it again very carefully. I release it with the robotic arm. Again, got to back away without tapping it so that there's no relative motion between the telescope and the orbiter.
Like 5 seconds, remote switch is in auto,
3, 2, 1, release. And back and away.
I see you got it open.
So what I'm looking at is some camera views, and then we've got other people looking out the overhead window to give me some cues as well. So I have to not run into that antenna, not run into everything, and then once I'm clear of it, the commander will fire the jets on the orbiter and fly the orbiter away from the telescope. And what that looks like from our vantage is that the telescope is flying right overhead. And we have kind of a little sunroof in the top. Those are the overhead windows there. What you can't see in this view is all of us kind of ducking down because it is so big and it looks so close to us. But we're all kind of crowding around to get one last view of the telescope. This is the last time probably that people will ever see it. So it was a pretty special moment for us, and we were feeling pretty good. All of the instruments had gone through their engineering checks well, and of course their science checks would take a couple of months. But it's, of course, still up there doing its thing, and I'll show you some pictures from that in just a few moments. But the next thing that we had to do was get out of that higher orbit. We're about 300 miles up, so we had to do an orbit adjust burn to get a little bit lower where there's a little bit less space junk and less likelihood of us getting hit by something. So that's what you'll see in this next view. Watch the floating space shuttle and watch what happens. I have to duck to avoid getting smacked by it as we fire the jets on the orbiter.
Mark. Engines are up.
Little duck there, goes right over my head. So that's kind of our day-to-day tasks now that we're done, and I'll show you a little bit of what it's like just to live in space. One of the favorite things, of course, is looking out the window at the Earth. We do have a beautiful planet, and it's really an incredible vantage point. This is supper time. One of the only times we got to eat together was after all the work was done. You can see that John decided he was going to eat dinner on the ceiling that day, just to be different. And here's Drew Feustel. He's making a burrito for dinner. We don't take bread into space because it makes crumbs and it get up your nose and in your eyes. And we use tortillas for pretty much everything. So you can see he's just stuck little packets of food to the wall as he makes his burrito. And then he's ready to eat. It's good stuff. This is our pilot, Greg Johnson, getting some exercise. He decided he was going to bicycle across the United States. Only took him about 10 minutes. You can guess what this area is. Hey, that's the space toilet. Now you know what it looks like. Everyone always wants to know. It's a little closet. You can guess what the tube is for. And you can guess what that's for. We'll just leave it at that. We did have a piece of equipment fail underneath the deck of the orbiter, and even though I'm an astronaut, I also have to be an air conditioning repair woman as well. I had to go mop up a bunch of water that had balled up on the humidity separator, and we took the opportunity, that's the humidity separator there, we took the opportunity to have a look around kind of at the guts of the orbiter. We don't get to do that very often, so pretty neat to see all of that. This is what it looks like when we sleep. We basically pin our sleeping bag to the wall. You strap yourself down, you strap your head down, your arms do float up, though, because there's nothing there to hold them down. Looks like a room full of mummies, basically. Here we are having fun with our food. Fluid dynamics experiments. That is Tang. There's Mike about to eat his water. Oh. And there's some very important physics experiments that we're conducting here. What's going to happen when he straightens his legs? It's going to slow down. You guys know that. Here we are playing the only video game that we fly with us in orbit. It's actually a way for the commander and pilot to practice their landing. The orbiter is a glider, so there's no go around. You get one shot at landing correctly. So you can see he's got a digital display there that looks like what his digital display will look like the next day as we're landing. We actually went around and around and around because the weather in Florida was bad, so we had lots of time to take a nap. This was a safe nap. Nobody drew on me. You can see we're just hanging out on the wall there. It's also extremely cold the last couple days that you're in space. We cold soak the orbiter because we build up a heat load as we come in, so I did have my UCLA sweatshirt on pretty much all the time. It is hard to get into your launch and entry suit for re-entry. We call it the pumpkin suit for obvious reasons, so you have a help there getting back in. And we had some time. We kept going around. We were waiting for a go for the deorbit burn, so you can see Scooter singing for us there, but I don't think too much of his singing ability, so... But there we are, strapped in and ready on the flight deck. Here we are after the deorbit burn. We're coming back in, of course, through the atmosphere, and you can see the orbiter tail there heating up. The orbiter hottest part gets about 1,600 degrees C as we're coming in. But we're nice and cool in the flight deck there since we did our cold soak. So we went around the Earth 197 times, 5.3 million miles, and we're finally getting ready to land at Edwards Air Force Base in California. Like I said, the weather in Florida was no good. But you can see the heads-up display there showing the commander where the runway is so he can get a nice lineup. And fortunately, we have really the best pilots in the world landing this thing. It's 200,000 pounds. It's coming down at a 17-degree glide slope. Normal airplane is about 3 degrees, so you are racing at the ground. And there we are with touchdown. You'll see the chute come out to help slow us down since we are pretty massive. Even though the runway's a few miles long, we do need that little bit of extra help. So we were pretty delighted to be back on Earth after those 2 weeks, after a successful mission, and really looking forward to that first shower. The telescope, of course, is still up there, and I have some images to show you that are from the what they call the early release images to show basically what the telescope is capable of now after the servicing mission. This is called the Butterfly Nebula for obvious reasons. It looks like this very delicate, beautiful thing, but it's actually roiling cauldrons of gas that are more than 36,000 degrees Fahrenheit, and that gas is shooting out of there at about 600,000 miles per hour. It's about 3,800 light years away. This one shows the capabilities of the new Wide Field 3 camera, which goes all the way into the infrared. There are young stars inside this cloud of dust that you can't see in the visible light, but when we go to the infrared light, you can see them right there and the jets of material that they're shooting out. So it's a pretty remarkable capability that they have now with the all the way into the infrared spectrum. The Space Telescope Imaging Spectrograph was the other instrument that we talked about repairing, and here's basically an example of the kinds of data that comes out of that. This is showing a huge, basically a starburst. It's shooting out all of this material, and it's showing you what that different material is going back to an explosion that happened like in the 19th century. This is one of my favorite ones, a globular cluster. If you were on a planet in this area, the night sky would be over 100 times brighter than it is in our own night sky. And you look at how many yellow suns there are in this picture, it's pretty mind-boggling. So it was pretty neat for me to get to be a part of that mission and be a part of something as remarkable as the Hubble Space Telescope. So I just was really grateful for that opportunity. And I'm also really grateful to UCLA for helping me get prepared for something like that by encouraging participation in practical, hands-on technical problem solving really early in my engineering career. I know that as engineers, your schedules will be absolutely crammed full of required coursework, but you really must take charge of your own education and find or create these type of team learning experiences for yourself. And if you can't find a club that appeals to you, you can create a new one, and the School of Engineering will help you out with that. And if anyone out there decides to resurrect the UCLA human-powered submarine team, I promise you I will turn up at the races to cheer you on. Thank you very much.